So last few weeks we have been seeing how to do, we learned few things, right? Multiplicative weight method, multiplicative weight method, primal dual, and 1 over epsilon q log n pass order n tilde order n poly log n space 1 minus epsilon approximation algorithm to maximum matching for max matching. Okay. All these algorithms are much like all these methods are way more general than what we have applied to. So this method has utility in both algorithmic game theory, economics, and whatnot. This has in solving combinatorial optimization problem as well as approximation. And what we saw is just one application of this methodology. There are other applications like B matching and other things, right? Imagine that now you're trying to do some sort of primal dual in streaming setting. So that's what it allows us to do. Okay. Good. So we'll change track and move to something very different today. Okay, not different, but at least not this technology, and move back to greedy algorithm. So there's some problem called maximum coverage problem. So what is a maximum coverage problem? Is that you have been given input is universe and some family of sets, and at number k, okay, output k sets that cover maximum number of elements. That cover maximum number of elements. Okay? I want to find cases such that their union covers maximum number of elements. Okay? We would like to make an approximation algorithm for this. It's an NP-hard problem. Approximation algorithm for this. Have you seen an approximation algorithm for this? So what should be the most obvious algorithm to try? Huh? What do you mean by largest set? But when I'm okay, so first time I do that, maybe I should have put some weights, maybe it doesn't matter, but second time, does it make sense? First time I pick the set with the maximum cardinality, but what about the second time? Does it make sense to pick the set with the maximum number of maximum cardinality set? Imagine that I picked up this set, and next set, which is the largest cardinality, is like this. So at least this approach, I mean, this shouldn't be giving us something. I mean, I can come up with an example where this will not give us any reasonable factor approximation algorithm for our problem. So what should be the most obvious approach? Huh? Among the cover element, pick the set which covers the maximum number of elements. Okay? So like, there's nothing. So here is a greedy algorithm. Okay. So this is, let's call it greedy cover u comma f comma k. Okay. So what do we do? So repeat, pick a set, okay, that covers a maximum number of, pick a set that covers the maximum number of uncovered elements. Number of uncovered elements. Okay, so this is the first thing. Okay, mark all the elements in the selected set as covered. Right? So that's it. Repeat until done. Initially we had K, now we are going to do this with K minus 1. Right? So while you just pick K sets if you can, I mean, if already you have covered all the elements, that's great, right? But you just stop. But the question is, what do you think is an approximation factor from greedy? Approximation factor for greedy. Any guess? Okay, let's see what we achieve. Okay? Let's see what we are able to achieve in this. So let opt denote the optimum value. Opt denote optimum value. Okay? Let opt denote the optimum value. And let xi denote the new elements that the set selected by greedy covers. Right? Maybe they're already covered elements, but let xi denote the and let's denote yi equal to summation 1 equal j equal to 1 to I. It means up until ith step how many elements we have covered, okay? And zi is opt minus y I minus 1, okay? Or let's call it yi. Okay. So here's my simple claim. What can you say about xi plus 1? How many new elements will xi plus 1 be covering? There are so many new elements left. Like opt covers this many elements, right? So look at what happens. So opt covers certain number of elements, right? Now certain number of elements are uncovered, and how many numbers of uncovered elements are there? Like with respect to opt, not we are not covering all elements. So your universe could be huge, okay? And opt covers some fraction of elements because we are only allowed to pick k sets, right? So suppose this is what opt covers, okay? Like whatever that means. Now, at this point of time, some elements here are uncovered. How many elements are uncovered? Zi elements are uncovered. Okay? Zi elements are uncovered. Now, opt picks some k sets. S1, S2, S3, dot dot dot, say Sk. These are the k sets opt picks, opt selects. Now, up until now, you might have picked up some sets in your solution, but the remaining guys has not been picked up by my greedy sets. So suppose this is not right, S2 is there, maybe S5, like some of these sets are already picked up by greedy algorithm, right? Now look at the remaining sets, okay? So let's call this sets solution S star. Let's consider S star minus sets S1 tilde, S2 tilde, dot dot dot, Si tilde, sets selected by greedy. Now let's just concentrate on these sets. Definitely these sets, if I would have picked up these sets, I will definitely cover all these elements, right? All these. It means at least one of these guys will be covering at least 1 by, so it means this implies by pigeonhole principle there exists Sj in say S star that gives Sj in W such that W covers at least Zi by k elements. In fact, k minus W, which is greater than or equal to Zi by k elements. Do you agree to this? Right? I mean, so what does this imply? But at this stage, all the sets in W are present to the greedy to choose. And what does he choose? He chooses the one which covers the maximum number of elements. It means we can say that xi plus 1 is at least Zi by k. Right? So the number of new elements that my greedy algorithm covers in the k plus 1 step is at least as much as optimum would have covered, like look at the remaining elements divided by k, right? Because there is a way to cover this much of elements by some set, and I choose the set which maximizes the number of uncovered elements. So this is very clear that xi plus 1 is greater than or equal to Zi. Okay? So this is a proof by picture or whatever you want to say. I mean, this is the proof. There's nothing, I mean, I wrote much more than the proof is required. Okay. Okay. Now, so this is it. So this is done. Now, so let's just keep them. Yeah. Here's my another claim, which is quite interesting, and this will appear several times in different contexts. Okay. So here's another claim. What is my claim? Is that xi plus 1 or zi plus 1, this Zi plus 1, number of elements which are yet uncovered, is not too much. Okay? What I mean by this, that look, I have to prove, if I can prove that number of uncovered elements at the after kth step is not too much left, right? It means I have covered large fraction. If I can tell you that Zk is at most 1/3 of opt, then what does it mean? If I can show that Zk, say, if I can show that Zk, right? I have picked up k sets. So suppose I can show that Zk is like 1/3 times opt. Then what does that imply? That implies that Yi is at least 2/3 of opt, right? It means it's like 1/3 approximation, right? So getting a lower bound on Zk gives us a approximation algorithm. So how good we are going to get an how good upper bound we are able to get Zk? Agreed? Because this just tells us, Zk tells us how much far away you are from the opt with your greedy algorithm. This is exactly what it measures. So I'm going to claim that Zk is nothing but okay. So I'm going to claim Zi plus 1 is less than equal to 1 minus 1 by k to the power I plus 1 times opt. This is what I'm going to prove by induction. By induction on I. So what is I equal to 0? What is I equal to 0? I equal to 0 is like Z1 should be less than equal to opt minus opt by k. Right? This is what it says, right? Z1 should be less than equal to opt minus by opt by k. But what we have shown, xi plus 1 is greater than equal to Z1 by k. But what is Z1? Is opt minus something, right? It is opt minus x1, right? So what we know is that opt minus Z1 is equal to opt minus x1, okay? Now x1 is at least this much. So what does this imply? This quantity is at least opt minus opt by k. Is that correct? What is Z1? Yeah, that's fine, right? No. This is, look, what is Z1? Is opt minus Y0, right? Y0 is empty set, right? So Z1 is opt minus Y0, which is equal to opt. Okay? So Z1 we start with opt. So now why this is, okay, what are you saying? Isn't this correct? Xi is at least this much, right? So you are saying this should be less than equal to? Right. Because you might be removing more, right? You might be covering more, but this is what it is. But then we have got, right, what Z1 is less than equal to opt minus opt by k, and we are happy. Done. Now let's look at the Zi plus 1 step. So what is Zi plus 1? Is less than equal to, what is Zi plus 1 less than equal to? Look, Zi minus xi plus 1. Yes. you are right. So there is nothing to prove here, no? Okay, you are right. So Z1 is equal to what? So if I put I equal to 0, Z1 is opt minus Y0, which is opt, which is definitely less than equal to. This is where. What should we do? So wait. So we shouldn't be Z0, right? So this is not correct. This is Z0, right? Yeah, this is fine, right? Look, Zi is opt minus Yi. So Z0 is opt minus Y0 is equal to opt, right? So Z1 is opt minus Y1, which is equal to X1. So equal to Y1, which is equal to opt minus X1, and this is correct. Okay. Now let's look at Zi plus 1. Okay. What is Zi plus 1? Zi plus 1 will be opt minus Yi plus 1. Right? Correct? Opt minus Y plus 1. Now, okay, fine. Now, this is equal to opt minus Yi plus Xi plus 1. What is the definition of Yi? No, this is where it goes wrong, right? So, like total number of new elements covered. So why should I write Y? Okay, so this is what it is. Right? Now this is opt minus Yi minus Xi plus 1, right? But opt minus Yi so this is equal to Zi minus Xi plus 1, right? So Zi plus 1 is exactly equal to Zi minus Xi plus 1, right? Because Zi plus 1 is opt minus Yi plus 1, which is nothing but Yi plus Xi plus 1. So which is opt minus Yi minus Xi plus 1, which is Zi minus Xi plus 1. This is perfectly valid because up until now, how much was the difference? Now I have covered more elements, so this is fine. But now Zi, I have induction hypothesis, right? By induction hypothesis, what is Zi tells us? Right? Zi, I can say, is 1 minus 1 over k times I times opt, right? Minus, what is Xi plus 1? Is Zi by k. Agreed? Maybe I should replace it here. Okay. So Zi by k, which is equal to Zi times 1 minus 1 over k, right? Right? So now if I apply induction hypothesis, I will get 1 minus 1 by k times I times opt times 1 minus 1 over k, which is equal to 1 minus 1 by k I plus 1 times opt. This is less than equal to, because we used induction hypothesis. Agreed? Okay. So now what do we have? So what is zk? So zk is less than equal to 1 minus 1 over k to the power k times opt, which is nothing but less than equal to 1 over e times opt, right? So hence yk, what is yk, right, is at least 1 minus 1 over e times opt, right? Just apply, right? Zk is whatever, right? Because here, right, so you can take it here, right? So what is yi? Yi is equal to opt minus zi, which is greater than equal to opt minus 1 over e times opt, right? Because this is an upper bound on zk. So yk, zk, this, which is equal to 1 minus 1 over e times opt. Okay. So if I do greedy, then this is good, and it covers how much? It covers 1 minus 1 by k fraction of 1 minus 1 by e fraction, which is like roughly, if you notice, 0 point some 632 opt. Okay. Okay. So this is called maximum coverage element. Now suppose I wanted to do set cover. I wanted to cover all elements, and I knew the opt. I knew k. Right? I knew k. I can guess k by doing some binary search. I guess the k. I run this max coverage element. How many fraction of elements have covered? Look, opt covered everything, right? And I have used opt sets greedily, and this analysis tells me that it covers 0.632 of the opt. So it covered 0.632 of n. I run it again. It will cover 0.632 of remaining guy. So how many times can you do this? Some log n time, right? And this is why you get set cover as log n approximation algorithm. Okay? Okay? And in fact, it is 1 by e. So this is why you get log n plus 1. You look very confused. No? Huh? Because it is 1 minus 1 by e. So how much is left after that? How much? How much is left after that? I have already covered opt by e. Right? So next time how much will I cover? 1 minus 1 by e of opt by e. Right? So I'm fractionally covering. Right? And so how much round do I need before nothing will be left? Imagine yourself that you covered half the element with opt sets. Next also you will cover half the sets, right? Half the elements. So opt plus another opt by, so for the next version, what is opt? Opt at most opt by 2. And opt is n. So log n times. But since we are covering much more, we are covering, what is left is point some 3, like opt by e is left. So this is like you will go to log n, not log n, but log n, because you're covering much more elements. Okay. So this analysis also tells us, okay, so what did we get? So we got, so let me write it down somewhere, couple of theorems, and we will see this analysis time and again. Okay, so what did we learn from here is the following. This is the theorem which we proved. Theorem. greedy coverage is 1 minus 1 by E, 1 minus 1 by E approximation for maximum coverage problem. Approximation for max coverage problem. Max coverage. And ln n plus 1 approximation for set cover. So this is an alternate analysis for set cover. Okay, so this is just an alternate analysis for ln n plus 1 for set cover. And you could have, if you had weights, you will cover the set which maximizes the utility of per element. I mean, is maximum or something of this nature, because you are looking for minimum weight set cover, right? So you just don't pick the set which covers the largest, but you pick the set which utility is larger, and that's it. Okay, so this was all about, and what we know as a lower bound. So lower bound, so unless I think unless NP is in D time n big O of log n, no 1 minus 1 by E minus epsilon approximation for max coverage, and no, I think no alpha ln n for, okay? No ln n, no ln some alpha ln n approximation for set cover for some alpha. Okay. Okay. Okay, so let's do a slightly different analysis for set cover, just for a different reason, okay? But you understand the intuition, right? By coverage, you cover good fraction. So, I mean, if you cover any fraction, you will go to some order log, and that's it. Okay. So, let's do another one. So, I'm just doing for set cover, and I'll tell you why I'm doing this. Okay, you will understand. Okay. Let K star be the number of sets in optimum set cover. And I'm doing cardinality version for now, just, I mean, it doesn't matter. Right? So, what does it mean? It means that optimal solution to max coverage problem for K equal to K star will cover all element. Agreed? Right? So if K star is a number of sets in optimum set cover, then if I set K equal to K star, then it will cover all elements, because there is a set cover instance. and zk star will be less than equal to n over e. Like zk is 1 minus 1 by k to the power e, 1 over e of opt. Opt is n. So zk star is going to be n over e. If you are going to run this greedy algorithm, okay? So similarly, after 2 times k star steps, two times k star steps of greedy cover, what is z2k star is less than n over e square. Right? It is 1 by e of n by e. So look, how many elements are left? N by e. I have run another round. So 1 by e of current thing. So this is why you get what you get is that greedy cover is a log n plus 1 approximation for set cover. Okay. So now so this is the intuition which I have been talking about up until now, and there is a reason why to do this, okay? Okay. So let's do a formal proof. So we know that Zi is like 1 minus 1 by k star times I, okay, times n, and after t equal to say k star ln n over k star steps, right? So now I am doing is k star times ln n by k star steps, okay? How much elements are left? So look, so after t, I mean, if I substitute this steps, how many elements will I cover? How many elements will be left to cover? What is z t? Can you tell me? So zt is less than equal to 1 minus 1 over k star times k star ln n by k star, right? This is what we say. But we also said that this time is n over e square. Great. So let's use that to say it is n by e to the power ln n over k star, right? Which is same as n over n by k star, right? Which is k star. Look, after 2 rounds you have e square element, n by e square element left. So after these many steps or these many rounds, I have this to the by this, which is n by k square. So k square sets left. K square elements to cover left. Okay. So how much will you take then? Okay. So after this step, greedy will cover at least one element, no? Right? After this step, greedy covers at least one element, and hence what will we get? Hence, how many sets does it pick? It picks k star ln n by k star plus k star sets. This many sets. Now if I take k star common, what do I get? Ln n over k star plus 1, which is less than equal to k star ln n plus 1. Okay, done. Okay. But why did I do this analysis is for the following reason. Assume that we have an instance of D set cover, right? Meaning each set in family has at most D elements, right? So now let's go and look back at this. Okay? Let's go and look back at this approximation and do this analysis. What is here? K star is at least n over D. In this case, each set can cover only D elements. So you at least need n by D's, n by D set. No? So you have a lower bound on K star. Great. Now let's use the lower bound here. Okay? So hence, ln n over K star is less than equal to what? Ln D. Right? So what does this imply? This implies we have ln D plus 1 approximation for D set cover. So this is a little uncommon, but it's the same analysis which gives us, so I thought let's just do it. Okay? So you have heard of ln D approximation for if the sets are small, and this is because of this. Okay? Okay? I did nothing, and this is why I just broke my analysis into two parts. First, because for this there's like a completely different analysis which I always get confused, is that you just break till n by k square, and then you have just k star elements left. You use k star, then you will only use ln n plus 1. That's fine. But for D, you get ln D plus 1 by just assuming the fact that you have better lower bound on the solution size. Okay? All good? Excellent. So we have done a maximum coverage for. It's not obvious for us that if these elements are coming in stream, and suppose it's only insert only stream, and I wanted to cover k sets, k elements that covers the maximum number of elements, it is obvious that we will be able to do it. Look, what did we do at any point of time? Our greedy algorithm is very simple. At any point of time, it picks a set that covers the maximum number of uncovered elements, right? Now, if I wanted to do a maximum coverage for, like in streaming, sets are coming and you can see them, whole sets, it's perfectly fine, but I want you to give me a guarantee, right? So if set has gone, right, if some set has gone, I don't know in future someone will come which will cover this much or not. So what should I do? You understand my issue? If I try to do this analysis, if I try to do this greedy, in, if we try to do this greedy in streaming fashion, right? We have difficulty because when sets are coming, I don't know which set to keep, right? Because it was completely dependent on, oh, I know my universe. So suppose I told you all the universe also for all that you know. Universe is from 1 to n. It has been told to you, and the subsets are from 1 to n. I do not know which set to keep, which set not to keep. If I just try to mimic this greedy algorithm, right? Because if I keep something here, but its analysis tells me something more interesting. Its analysis tells me something that might be useful thing to think, right? Hoping to cover everything is not important. We used a small lemma, our first claim, where when we were trying to set up everything, we said that xk is greater than zk, xk plus 1 was greater than or equal to zk, or something of this nature, right? We said this. Yeah. So what we said is xi plus 1 is zi by k, right? And we gave a proof for this, right? And all we did in our analysis is use this fact. So why not make that as a basis of my greedy algorithm? At any point of time, if I did the following change in my greedy algorithm, okay, if I did my change, pick a set that covered some maximum number of uncovered elements. I said pick a set that covers at least zi by k elements. Suppose this is all, I mean, like I make this as a part of my analysis, then it's perfectly fine for me, right? I do not have to look at this. I have to look at locally. Are you covering 1 by k fraction of the sets or not? And if it does, I keep it, and I'm very happy. Will this now I have much more chance of succeeding, because at any point of time my set comes and I see that it covers at least 1 by k fraction of this. I keep that. Right? So I'm keeping sets anyway. So since I'm keeping sets, I also know uncovered elements, right? So for the uncovered elements, if there is anybody comes which covers certain fraction, then I keep it. I don't care about. And the first time I see this, I keep it. My whole approximation ratio will go. Like, will analysis change at all? Nothing. This is my good old streaming algorithm, right? I just use the fact in my analysis that it is good for us to choose a set that just covers of the remaining elements 1 by k fraction of it. Right? So this will work. And this should give us 1 by e minus, like, and this will also give us a like 1 minus 1 by e approximation factor. I mean, I think so, but we have to just check. Okay? This was not part of the syllabus, so this is whatever. So this is a good exercise to check what happens if we replace this guarantee with this, because now it's easy for us. I have a universe. I know 1 to n is my universe set. So it's like takes n log n space for all that I care, right? It takes n log n space, right? And I'm going to keep another, it will take, if I'm going to keep, look, if I'm going to keep sets also, it can take n polylog n. Like, it can take me n log n time root n sets or something. I don't know. I mean, like, it can keep, you understand? But if I just wanted to return you the number of sets I need, That's very easy with n log n, right? I just cross out. Look, for one set I anyway would take n log n space, right? So if that is how much, and I'm happy with the number you provide me, right? I'm happy with the number you provide me. Then that's very easy to maintain in n log n spaces. Because what? I keep this universe, whichever element is covered, I just cross that. Like I keep a Boolean vector n, and if it is covered, I make it 1, like, right? So if any new sets comes, I can just run it over it and see how many elements it covers. If for all zeros it is, look at the number of zeros element it has. If it is 1 by k fraction, right? Then I pick it, otherwise I just let this set go. And whatever number comes, I return you this number. And I'm guaranteed that then this, I can implement all this in order n log n space in one pass, right? Order n log n space, one pass, and 1 minus 1 by e approximation. And since we can't do better in a static setting, we can't hope to do better in streaming setting. Okay? So this algorithm should give you some intuition how to go about things, right? So sometimes it's analysis which helps us look for the right key ingredient in streaming algorithms, not the greedy. Look, largely it is a greedy algorithm, but maybe what obvious thing a greedy keeps is not important. So in fact, this itself is a greedy algorithm, right? And notice one thing, this will also reduce the running time. Like even for the static setting, this will reduce the running time. I don't have to, like every time I don't have to go through all the remaining sets. Like one pass over the sets and maintaining some sort of data structure will help us do this. So whatever, okay, fine. Okay, but that is not what the agenda of the item was, okay? So the agenda item, this was just to motivate you to the kind of problems we are going to consider now, and nothing more than that, okay? Also to make you aware of these analysis and do some things, okay? So, okay, I will leave this because this is the fulcrum of our analysis. Okay. So what we are going to do is something called submodular, like submodular optimization, okay? So first, what is a submodular functions? If you have done parameterized complexity, you have seen important cuts, important separators, and that is via submodularity, okay? So basically, suppose I have a comma b, some subset of n, and I have a function from 2 to the power n to reals, for example, okay? Then what submodularity definition actually tells us is that for any a comma b subset of this, f of a plus f of b is at least f of a union b plus f of a intersection b. So this is what is generally considered definition. But there are many variations of definition, okay? And for our purposes, it will be much more important to look at the other equivalent definition than this, okay? So what is an other equivalent definition? This is called marginals, okay? Marginal contribution. So given a set function, f, okay, given a set function f, a set S subset of n, and an element u in n, okay, u in n, the marginal contribution of f of u to s, okay, marginal contribution u to s with respect to f is defined as right? How much utility do I get by adding u to set S? Okay, so this is what is called like, so set S was giving me some amount of utility, some amount of contribution. So this is why you will see this kind of function appearing a lot in game theory, because it's like, or statistics where people consider marginals. It's like, okay, after adding this, what is the marginal benefit do I get from this? Okay, and why we should be interested in such kind of definition, because if we are trying to optimize some sort of submodular function, then we would like to, given a set S, I mean, does adding this element helps us getting enough marginal contribution or not is a natural greedy approach to try. Like at any point of time, I would like to add a set. Suppose I want to find a set A which maximizes some function, right? Where A is a subset of n and I have partially constructed. So at any point of time, I would like to add something to the set whose margin is best, right? I mean, this is very much. So this is why this is a definition which we would like to use. So what is it? What is an equivalent definition? Is the following. So this is the lemma. Okay. A set function f is submodular if and only if. So this is my definition of submodularity. Okay, if and only if for all A subset of B subset of n, okay, okay, and each u in n minus b. So I pick up an element which is in n minus b, the following holds. What is the following holds? The marginal contribution to A, marginal contribution of adding u to A is at least marginal contribution of adding u to B. So larger the set, okay, marginals keep decreasing. So you have larger the set and you try to add an element to that, right? So its marginal will decrease, okay? And if you think of, I mean, so this is the definition of what is someone. So of course we need to prove this. This is like, it's not obvious statement, okay? But do you think any, look, there are two kinds of proof. One, which we will do now, which is basically like writing down inequalities and hoping that they just work out magic. And the other is that we really understand what is this that adding. And so I'm giving a proof which is like, which should explain to you why this is the right way of looking at submodularity. So forward direction, there's not much, okay? I just have to apply these things with some correct A and B, okay? So now let's say I take A tilde as A union E, okay, or U, and B tilde is B. And now let's apply this function. So what does it tell us? It tells us f of A tilde plus f of B tilde, okay, is at least f of A tilde union B tilde plus f of A tilde intersection B tilde, right? And what is this? So what is f of A tilde union B is basically f of B union U. right? Because A is a subset of B. And what is f of A tilde intersection B tilde? Is f of A. Okay. And what is this equal to? F of A union U plus f of B. Right? And now let's take the inequalities in the right way. So what we have to show? So take A this side. So it says f of A union U minus f of A is greater than or equal to, right, f of B union U, right, and minus f of B, right? But what is it? This is exactly the definition of utility, right? So this is utility with respect to A is greater than or equal to utility with respect to B. Okay. That assume that for all whatever, for all A subset of B subset of n, U in n minus B, utility of A is at least utility of B. Now suppose I have a set C and suppose I have a set D, and I would like to show this inequality for them. Good. So now let's write it down in this. This is D minus C is D1, D2, dot dot dot, say DL. Okay? DH, I don't know, whatever. And I'm going to write DI is D1 to DI. Okay? So let's now consider f of D minus f of C intersection D. Okay? Is equal to what? I'm going to write it down slightly differently this, like adding marginals, okay, one by one. Okay, so what I'm going to write, I equal to 1 to h. Okay, so first I add, so I start with, did I write correctly? Yeah, this is fine. So I construct C intersection D is here. Okay, and gradually we'll try to make stuff. I think okay, let's see. F of C intersection D is what? This. This sounds. C intersection D union DI minus F of C intersection D union DI minus 1. Okay? And say D0 is phi. Okay. Okay, so what is happening here? So I equal to 1, what am I adding? D1, and I am subtracting what? 0. So basically, if you write it down clearly, so this is basically a telescopic sum, right? Because it is C intersection D union D1 minus F C intersection D minus union D0. Okay, this is the first term. What is the second term? It is going to be 2 C intersection D union D2 minus F C intersection D union D1, right? So this and this will get cancelled, okay? Okay. Now what will be the last term? So F of C intersection D, okay, union DH minus F of C intersection D union DH minus 1. This is what it is going to be. And now if my understanding is correct, everything will get cancelled except this term and this term. Right? No? Now, what is FC intersection D union DH? This is basically F of D, right? C intersection D, and I have added this. So this is perfectly correct. Now, and what is this term which is remaining is C intersection D union D0, which is empty set. So this is definitely FC intersection D. So this equality holds, right? So I have just written some telescopic series, cut this off. Okay, fine. Okay. But look, what does it mean? That even if I have a bigger set, I could write things in terms of how these things are added one by one with respect to their utility. Okay, so this is what he's trying to show. But now, what is this? Summation I equal to 1 to h. What is this in terms of utility? What is this in terms of utility? In terms of utility, if you notice, this is basically what I'm saying is f, I'm adding di, C intersection D union di minus 1. This is exactly what it is. So if I added an element di to this set, this is a utility I'm going to get. Okay, good. But now, this is greater than equal to, I could write anything here, no? So in particular, I can write this is summation going from I equal to 1 to h, f of di, C intersection di minus 1. Right? Because C intersection D, what it says? Look, for all AB, A subset of B, this marginal utility is larger than this. So definitely C intersection D is contained inside C. Okay? Now, if you write it now again, what will you get? If you expand this again, what are you going to get? So if I write down the definition of this, which is like, okay, fine. So this is going to be f of C union D1, right? D1 minus f of C union D0 plus f of C union D2 minus f of C union D1 dot 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 plus f of C union DH minus f of C union DH minus 1. Do you agree? Everything again will get cancelled except which term? This term and this term. These are the only two things which will survive, because everything else will telescopically cancel each other, right? This will cancel to this will cancel to this will cancel to this will cancel to this. So what are we left with? Okay, so what is f of C union DH? C union DH is nothing but f of C union D. So this is equal to f of C union D. And what is f of C minus f of C union D0? Is f of C, right? So now this implies f of C plus f of D is equal to f of C union D plus f of C intersection D. Yes, it is. Yeah, because of this. Fine. Okay. So for all our purposes, this is much better definition than this normal definition. So like this is sort of local definition of submodularity. You are given me two sets. If I add, how things behave. Okay. But there are even more local definitions. But I'm not going to prove its equality, but let me still state it because you might find it useful in some other purposes. Okay. So given that now this is it, so I'm going to rub this, okay, and I'm going to write it down, this particular definition, which is going to, I have shown to you that they are equivalent definition. So now I can use the following, right? Submodular function f is from 2 to the power n to some r, and for all a subset of b subset of n e in, for all a subset of b and u in n minus b, f utility a is greater than or equal to f utility b. Okay, this is it, where f utility a is f a union u, or let's say f x union y is f x union y minus f of y. Okay, so this is just a symbol. So another local definition, which is again equivalent to all these things, even more local definition. For all a subset of n, okay, and I comma j in n minus a, this tells you, you add I to a, add j to a, and this quantity is at least you hope for okay. So try to prove that they're equivalent. Exercise. Okay. Okay. Can you give me some examples of submodular functions? Cut function. Okay. So given a graph G, right? Partial or doesn't matter. F from 2 to the power v z. Actually, this is to natural number union z 0, right? Okay, I'll tell you why. So what is this? F of x is partial of x. Edges leaving x. Okay, and if g was directed, I could also take f of x out arcs leaving x. Right? All these are example of submodular function. What about coverage function? So I have a universe 1 to n, okay, and I have a family of function. Okay. Will that not be a submodular function if I just take all the elements that it covers? Okay. So this function, okay, I mean it's up to me how I define, right? I mean how I define this function is like, so my function is going to be from some ground set, right? So I am going to define my ground set is, let's say u tilde is 1 to m. This is my ground set. Okay, and what is f of 2 u tilde? Now you tell me to say natural number, whatever. Okay, so what is this? F of x is union of I in x fi. That's it. But is this function submodular? A good question, no? Okay, this is this. Okay, and what about, so this is like set cover. Okay, but what about maximum K coverage? Okay, so if this is, then is this function submodular? Is this definition? Otherwise, it's very hard to show. Right? If you use the second definition, then this is easy. Okay, anyway, let's take a break and come back.